You're back.
No, it's recording.
Okay, great. So let me begin. Right, well, the idea behind this 15-minute talk is about doing science with ALeRCE. And obviously this is a huge area, and each tiny little individual science case could probably be devoted to 15 minutes, an hour. So I'm just going to very broadly touch upon many of the things you can do. So the sort of current scope of ALeRCE in terms of the current and future sort of ground that we're covering with alerts span a huge range of science topics, from solar system objects, so comets, meteors, variable stars, flaring stars, gravitational lenses, transients, both galactic and extragalactic, active galactic nuclei. And then, of course, this is a wonderful playground for trying to apply machine learning techniques that are already known, develop machine learning techniques that are not known, and so forth. And so one thing that, of course, emphasizes that we are working with alerts. And this means we're receiving them in somewhat real time, typically for ZTF, for instance, which is what ALeRCE is currently working with. We're getting them about a half an hour after they go off and the image is taken. And then it takes us a few minutes to classify them and then push them through. And of course, this opens up a really unique window for rapid follow-up. So being able to potentially observe the source within an hour of it being taken the first time. Another thing that the alert stream is good for is that it gives you direct access to difference images and difference image photometry. And this isn't necessarily part of the normal cataloging process as yet. And so if you go to ZTF DR3, their catalogs are done with force photometry. And so in some cases, you might want to access the alerts so you can get the difference photometry. So, of course, within each of these categories, there's a lot one can do. And so for solar system objects, really we haven't touched too strongly upon that within the ALeRCE team yet. But of course, there's multiple things that are going on here. One is just simply to find near-Earth objects, a fraction of which could be potentially hazardous asteroids that we might have to call Bruce Willis and have him go up in a rocket and set a nuke off on the asteroid to blow it up. That's sort of one thing. We found most of the big asteroids, we know kind of about them, but as you go down in magnitude here, we start to have some missing sources. This is an H-band, but you have a number of sort of smaller things that if they impacted the Earth, they could do some damage. They're not sort of extinction level events like here, but they're significantly stronger than Tunguska, which was a pretty heavy impact in the Russian sort of tundra. The other benefit, of course, is that if we know about near-Earth objects, we can send satellites there to study them, or space missions, and so we can go and grab material from something that might have actually been formed in the outer solar system, and so we can do in situ measurements as well. We can also, of course, characterize the main belt asteroids, Trojans, Trans-Neptune, Kuiper belt objects, etc. We can also look at comet families, a long period of the Jupiter family ones, and do space density, velocity density, compositions, rotation and surface features. And these all tell us, how these actually form and are part of the overall study of how our Milky Way or how our solar system is formed, and sort of lead to the solar system hypothesis. There's the variable stars and flaring stars, and so there's a huge sort of zoo of different types of stars, whether they be pulsating variables, stochastic variables, eclipsing binaries, and so forth. And so understanding the physics of the pulsation mechanisms, so the outbursting, the accretion, surface features, etc., using eclipsing binaries to unlock physical properties of stars and then kind of paint the HR diagram with them. Using variable and eclipsing binaries as stellar population tracers to study the global population in terms of age, magnetic activity, composition, star formation history, et cetera. And then microlens as probes of compact objects, potentially planets around stars and so forth. This is just an example of one alert that we recently had that we found that went, had a huge rise over just a couple of days. It was sort of puzzling. We weren't sure if it was a supernova. This was the counterpart in Pan-STARRS, a very faint, maybe blue object. And so we got a spectrum of it. And the spectrum, of course, shows H alpha here at more or less a systemic velocity. So it was a galactic object, turned out to be a galactic nova. And so there's all sorts of things lurking in the events that could be potentially interesting. If we move out beyond sort of galactic transients, which are kind of classical nova down here, LBVs, as we move out to extragalactic sources, there's a huge parameter space here, some of which has been explored in the past. So the sort of longer decay time events have been pretty well explored and established. So there's lots of well-studied cases of type 1a and type 2 supernovae, core collapse supernovae, lots of classical nova, lots of LBVs, reversible variables. But as you move to faster decay times, you go into classes which, rare classes which haven't really been studied so much, or very fast events which really haven't been studied so much. And so the whole field is kind of pushing in this direction to try and find orphan afterglows, find type 1a, dot 1a dot whatever these things are, macronovae, fallback supernovae, shock breakouts, and so forth. And so having alerts that are coming every few days that, there is going to be a subset of sources that they might only be seen once or twice and then they disappear. And so trying to identify those things and follow them up is really tricky, but that's where the whole field is kind of moving. And establishing optical counterparts for some of these theoretical classes like fallback supernovae. Then there's AGN. AGN, of course, are well known to be variable and have variability across a huge number of parameters. And so characterizing this variability is, say, a function of black hole mass, accretion rate, host galaxy, radio loud or radio quiet, environment, and so forth is something that people would like to do in better detail, and ideally building up samples of millions of objects where you have nice light curves, and you can explore this all the way down, for instance, to intermediate mass black holes. Maybe we can find some intermediate mass black holes in nearby galaxies, or out to high redshifts to see how sources at redshift 7 or 8 might vary. These are just some examples from a paper from Paula Sanchez-Sáez showing distributions of AGN, which are host dominated, versus QSO, which are nucleus dominated, and blazars, and sort of different parameter spaces, and being able to break them apart via, these are the things that are selected from the alerts. These are just a couple of very weird AGN showing dramatic decreases, for instance, by a magnitude in about 30 to, well, actually about more like 60 days. And then sort of strong variability, which is kind of abnormal in trying to understand this variability. And then, of course, there's the machine learning aspect of it. So, how to develop an ecosystem where we can sort of apply machine learning to this data set and try to expand the taxonomy to try and find sort of rare classes or break up classes, try to deal with unbalanced, unrepresentative training sets, how to deal with data augmentation using synthetic versus real data, how to implement domain adaptation. So learning from one sample and then adapting it to a completely different data set. And how to implement active learning. And then, of course, how to use machine learning to actually physically characterize these things. So, many deep learning results are often considered black boxes. And so how do you tie physical parameters or physical intuitive understanding to machine learning, and how to sort of deal with stuff in a probabilistic catalog? Yeah.
You have 2 minutes left.
Yes. Say again?
You have 2 minutes left.
Okay, fine. Right, so just an example of case use, ZTF triggers an alert, and you know, there's a nearby object, it was undetected the previous night, so this is our stamp. We get an alert, it goes to the brokers classify it, and they communicate with one of the target observation managers to trigger follow-up observations. You know, so we have a photometric confirmation. A few minutes later, it's a supernova, for instance. So then we go after spectroscopy, and so we trigger another TOM observation for spectroscopic observations, and so we end up getting spectroscopy within a few hours, and we say, ah, okay, this is interacting, this supernova is interacting with dense material, and we can see that. And so then we might trigger polarization observations, and we could all potentially do this in the same night if everything was really well aligned and the machine was oiled properly. And we could also trigger radio and X-ray and understand this object in a very fundamental new way. That would be the sort of ideal use case. So what we've kind of done so far is we have this early classifier, which you heard a little bit about, which classifies based on this first image stamp, and we do pretty well. Here we're just showing some statistics. So we've been able to classify, sort of do rapid classification of a few objects. And typically, you know, because we can identify just on the first stamp, we might get an advantage of 1 or 2 days over the next confirmation image. With the ZTF survey. And so this is kind of the up-to-date statistics in terms of what we've been able to sort of recover from the spectroscopically confirmed side. We're typically doing about 75% in terms of if we detect an object classified as supernova, it'll end up having multiple observations. This isn't necessarily to say that these are bad, they just might be at the faint end and are kind of difficult to detect through, you know, we might only be detecting them at the peak. And just some sort of examples of changes in magnitude and finding things very, very rapidly. Okay, we also have the late classifier. Again, we heard a little bit about that in the machine learning talk yesterday. But the idea here is once we have sort of 5 observations, we can kind of get a handle on what the light curve is doing. And we do pretty well in terms of classifying it into stochastic, transient, or periodic other. And then within those classes, we do decently, but we could always improve this a little bit. These are some of the example light curves that we have from these different classes. And this is the magnitude distribution we have for the labeled versus the unlabeled sets, which was a question which was asked yesterday. Okay, now the trick, of course, is to extend this. Right now we have labeled sets which kind of go down to the depth of ZTF. The trick is to extend this to LSST, which, in which case we don't have necessarily labeled sets, which will go all the way down. And so this is our current taxonomy. There's many things that are kind of missing here, which we're kind of investigating and trying to put in gray here. But it's a decently healthy and sort of dynamic taxonomy. So there are current challenges with working with the ZTF data. One of the challenges which you should be sort of aware of is there's a 5 sigma limit. And so there are variable things that are in ZTF which aren't detected by ALeRCE, because this is 5 sigma of the template versus the data. And so this means it's non-trivial to derive completeness and selection functions. And so ideally you have to go to the DR3 in order to do that. The upper limits that they provide at the moment are only global, not local, so there's no force photometry on the source. This will change in 2021 when they start doing force photometry. There's a lot of junk that's not caught by the internal ZTF identification or the real bogus classifier. So there's lots of satellites, there's lots of ghost reflections that aren't cataloged. The difference in the images aren't always perfect, there's dipoles sometimes. And so there's lots of cosmic rays that end up being blurred in the deconvolution and then passing through below the real bogus cuts. So there's some issues in working with the current data. This will all change as a function of time, and of course LSST will provide a lot of these things out of the box. So just kind of to summarize, you know, we're seeing astronomical data sets go through a rapid change, and we need to sort of fold in big data science methods and machine learning techniques into the sort of toolbox of the astronomer. The key impact of ALeRCE is rapid follow-up and access to the difference image photometry. So that's really one of the key advantages of working with them. At the moment, there's a large effort needed to compile and curate training sets, which we talked a little bit about in the day before. But this is kind of the new paradigm. So we're going to be kind of librarians for curating data sets and then using them to train models. So I think I'll end there and take any questions that you guys have. All right, and I guess this is just a lead into the tutorial. So we have the tutorial set up for today. There's a supernova notebook tutorial and the asteroid notebook tutorial, which are going to be simultaneous right after this talk. And then there's the 1 hour later, the variable stars notebook and the AGN notebook, which will be later. Okay, questions? I saw some here.
So in the chat, there are
no
questions for the moment. So maybe people can raise their hands if they want to speak up or write a question in the chat. Okay, it seems there are no questions, so maybe we can move up to the tutorials.
Great. So I think those are both under different links.
Yes, the link for the asteroid is different and it's in the chat. Also in the email that Francisco sent yesterday.
Okay, but the supernova one is happening here.
Yes.
Oh, there is one question, so please, Cristóbal. Okay, we don't have much time, so please be quick. How limiting is the 30 minutes time difference from observations to detection?
It depends on the science you want to do. If you're obviously going to disappear in 30 minutes, then it's crucial. But it probably affects a small amount of science cases. But you know, the faster you can get onto an object, the potentially more interesting science you can derive from it. So if, for instance, for supernova that are rising, if you get them really, really early on, you might see some the flash of the ionization of the material around it, and that will fade with time. And so the slower you are to get on it, the less likely you are to see those features.